Okay, friends, very good evening. Welcome back to the uh, RFIC Unit 4 classes. So, Unit 4, we are going to discuss about Class A, B, C, and AB amplifiers and Class DEF amplifiers, RF power amplifier design examples, voltage controlled oscillators, resonators, negative resistance oscillators, phase lock loops, linearized PLL models, PLL design examples, phase detectors, charge pumps, loop filters, and phase detectors, charge pumps, and loop filters. And now introduction. Let's see the introduction. In this chapter we study the problem of delivering RF power effectively to a load. Then the maximum power transfer theorem is largely useless in the design of power amplifiers. One mirror reason is that one minor reason is that it isn't entirely clear now how to define impedances in a large signal non-linear system. A more important reason is that even if we are able to solve that little problem and subsequently arrange for a conjugate match, the efficiency would be only 50% because equal amounts of power are then dissipated the source and load. So, introduction. Hence, instead of limiting efficiency to 50% by maximizing power transfer, one generally decides a PA to deliver a specified amount of power into a load with the highest possible efficiency consistent with the acceptable power gain and linearity. The drain efficiency or collector efficiency is defined as PL denotes the average power delivered to the load. P is SUPP, the average power drawn from the supply voltage. Classic power amplifier topology. There are four types of power amplifiers, distinguished primarily by bias conditions that may be termed classic PA. So, class A power amplifiers, class AB power amplifiers, class B power amplifiers, and class C power amplifiers. All four may be understood by studying the single model sketched in figure. That is follows. So, classic power amplifier topology. All four may be understood by studying the single model sketched in figure. So, in this general model, the resistor RL represents the load into which we were to deliver the output power. A big fat inductance BFL feeds DC power to the drain and is assumed large enough so that the current through it is substantially constant. So the drain is connected to a tank circuit through capacitor VFC to prevent any DC dissipation in the load. One advantage of this particular configuration is that the transistor's output capacitance can be absorbed into the tank, as in a conventional small signal amplifier. So, another is that the filtering provided by the tank cuts down on out of band emissions caused by ever present nonlinearities. This consideration is particularly important here because we are no longer restricting ourselves to small signal operation and must therefore expect for some distortions. Class A power amplifiers. The assumption in Class A design is that bias levels are chosen so that the transistor operates linearly. For a bipolar realization, this condition is satisfied by avoiding cutoff and saturation. For MOS implementations, the transistor is kept in the pentode region of operation. So, pentode region of operation. Class A power amplifiers. Although linearity is certainly desirable, the Class A amplifier provides it at the expense of efficiency because there is always dissipation due to the bias current even when there is no signal. To understand quantitatively why the efficiency is poor, assume that the drain current is reasonably well approximated by ID is equal to IDC plus IRF sine omega naught t, where IDC is the bias current. IRF is the amplitude of the signal component, where IRF is the amplitude of the signal component of the drain current, and the omega naught is the single frequency. Class A power amplifiers. The output voltage is simply the product of a signal current and the load resistance. Since the big fat inductor BFL forces a substantially constant current through it, KCL tells us that the signal current is none other than the signal component of the output voltage is simply the product of a signal current and the load resistance. Since the big fat inductor BFL forces a substantially constant current through it, KCL tells us that the signal current is none other than the signal component of the drain current. Therefore, V naught is equal to minus IRF or sine omega naught t. Finally, the drain voltage is the sum of the DC drain voltage. Tells us that the signal current is none other than the signal component of the drain. Therefore, V naught is equal to minus RF or sine omega naught t. Finally, the drain voltage is the sum of the DC drain voltage and the signal voltage. The big fat inductor BFL presents a DC shock so that the drain voltage swings symmetrically about VDD. The drain voltage and the current are therefore offset sinusoids that are 180 degrees out of phase with each other as shown in the figure. The drain voltage and current for ideal class A amplifier is looks like that. Class A power amplifiers efficiency, the signal power delivered to R is PRF is equal to I square RF into R by 2. IDC is equal to IRF. Let the transistor does not go to cutoff. Does not go to cutoff. Then so that the input DC power is PDC is equal to IDC into VDD is equal to IRF into VDD. Then the ratio of RF output power to DC input power is a measure of efficiency and it is given by eta is equal to PRF by PDC is equal to I square RF R by 2 by IRF into VDD. So is equal to IRF R by 2 VDD. What are the class A power amplifiers considerations? The maximum of IRF is equal to VDD, so the max efficiency is equal to 50%. Practically, it is 30 to 35%. In Class A amplifier, the maximum drain to source voltage is 2 VDD, while the peak drain current has a value of 2 VDD by R. The normalized power output capability, which is simply the ratio of the actual output power to the product of the maximum device out voltage and current. So Pn is equal to Pn is equal to PRF by VDS into PKID comma max, that is equal to V square DD by 2R by V 2 into VDD into 2 VDD by R, that is equal to 1 by 8. The power amplifier, Class B power amplifier is shown in the below. Class B power amplifier. So, Class B power amplifier, if the bias were arranged to reduce the fraction of a cycle over which drain current and drain voltage are simultaneously non-zero, transistor dissipation would diminish and improves efficiency. One way is switch off the output device for every half cycle. This operation is called Class B power amplifier. Exact 50% conduction is not practical, so pure Class B does not exist. It produces non-sinusoidal output, but it has good linearity. It operates in push-pull configuration with two transistors. Although the single transistor version of a Class B amplifier is analyzed here, but the most practical Class B amplifiers are push-pull configurations or two transistors. We assume we assume that the drain current is sinusoidal for one half cycle and zero for the other half cycle. The drain current ID of the form ID is equal to IRF sin omega naught t for ID is greater than 0. So drain voltage and current for ideal Class B amplifier should be like this. The Class B power amplifier. To compute the output voltage, we will first find the fundamental component of the drain current and then multiply this current by the load resistance IFUND is equal to 2 by T of 0 T by 2 IRF of sin omega naught T into sin omega naught T dt is equal to IRF by 2. I fund is equal to 2 by T 0 to T by 2 ID sin omega naught T dt. This is what the I fund is equal to 2 by T of 0 to T by 2 ID sin omega naught T dt. 2 by T is 0 to T by 2 IRF sin omega naught T sin omega naught T into dt. 2 RF 2 IRF by T 0 to T by 2 sin square omega naught T into dt. 2 IRF by T 0 to T by 2 1 minus cos 2 omega naught T by 2 of dt is equal to 2 IRF by T, that is 0 to T by 2 1 by 2 dt minus 0. Here 2 gets cancelled and IRF by T is into T by 2 minus 0. I fund is equal to IRF by 2. Class B power amplifier Vout is approximately equal to IRF by 2 into R sin omega naught t. Since the maximum possible value of Vout is VDD, it is clear from the above equation that the maximum value of IRF is IRF comma max is equal to 2 VDD by R. 2 IRF by 2. Class B power amplifier Vout is approximately equal to IRF by 2 R sin omega naught t. Since the maximum possible value of Vout is VDD, it is clear from above equation that the maximum value of IRF is IRF comma max is equal to 2 VDD by R. The peak drain current and maximum output voltage are therefore the same as for the Class A amplifier. Computing the drain efficiency as before, we first calculate the output power as P0 is equal to V0 square by 2R. The maximum signal amplitude cross R is V0 is not greater than VDD, so output power max is P0 comma max is equal to V square V square DD by 2R. Computing the DC input power requires computation of the average drain current. ID is equal to 1 by T into 0 T by 2 VDD by R sin omega naught T dt. So, ID bar is equal to 2 VDD by R into 1 by T into 0 T by 2 sin omega naught T dt. 2 VDD by RT of minus cos omega naught T by omega naught T by 2 to 0. The limits are applied. 2 VDD by RT minus cos of omega naught T by 2 by omega naught plus 1 by omega naught is equal to 2 VDD by RT 1 by omega naught plus 1 by omega naught, that is equal to 2 VDD by RT 2 by 2 pi by T is equal to 2 VDD by RT into 2T by 2 pi is equal to 2 by pi into VDD by R. Then ID is equal to 2 VDD by pi R. So that the DC power supplied is PDC is equal to 2 V square DD by pi R. So that the DC power supplied is PDC is equal to 2 V square DD by pi R. Finally, the maximum drain efficiency for a class B amplifier is eta is equal to P0 comma max by PDC is equal to pi by 4. The normalized power capability of this amplifier is 1 by 8, the same as for the class A. Since the output power, maximum drain voltage and maximum drain current are also the same.